clean room in the PHSF, and the folks are getting ready, and they're doing a lift of our spacecraft, and they are bringing it over to a ground GSE, a turnover fixture here, where they can move it around and manipulate it how they need to, get in the right orientations. This is the high gain antenna that is getting installed on the spacecraft for the very last time, and now they're using that rotation fixture to get into a different orientation for access to other parts of the spacecraft. This is all final launch processing activities down here at the Kennedy Space Center. Here's a view of our solar arrays, and checking them out before they're installed for the last time on the spacecraft. This is actually a test where they bring in current, and you actually light up the solar cells as noted there, or depicted there, and putting on blanketing. This is one of our many instruments. We have 8 instruments. It's the SWEA instrument that's on a boom, and we need to deploy everything one last time before launch. We've done this before out in Denver, Lockheed Martin Denver, but in this case we want to do it one last time post shipment. This is a big deal where we deploy the solar arrays, and hopefully in a couple hours we'll be on orbit and doing the same thing, and that'll be a configuration on orbit with it spreading its wings. And now they're doing a health check, so to speak, with what's called the Hollywood lights onto the solar panels, and that all went well. And now they're bringing in the solar panels for the last time, stowing it and getting it ready to be put into the fairing, and in a couple weeks later. This is a spin balance test, and rotating above 5 RPM prior to, again, buttoning it up in the fairing and moving it out to the launch pad.
Yeah, that was about the last thing before you put the fairing around it. So tell us a little bit more about what happens after it comes off the rocket today. What are the things that you're going to be looking for to happen, and when, and how will you know the spacecraft is healthy?
Sure. Some of the assets or components are already turned on, but others we'll be getting data shortly after. Within a minute or so, we'll be getting data from the spacecraft after separation, and we'll get an early indication of how it's looking. And then within 15 minutes of separation from the launch vehicle, the panels, the solar arrays will be fully deployed, and we'll get confirmation of that. And then we'll start into our overall checks, and within a couple hours we'll be be able to say, hey, everything looks good. And that's the hope. And I feel, the way this is tested out, it's looks really good at this point. But we've got a ride ahead of us, hopefully this afternoon, and we'll see how it checks out in a couple hours up on orbit.
All right. And the solar arrays, is that a command you send from the ground, or does the spacecraft do that on its own, begin to deploy the arrays?
It can take care of it itself. So yeah, so we'll be able to certainly get the data that says everything went fine. So and we're really excited to be at this point.
All right, Dave, thank you very much. And of course, we're looking forward to the launch and also hearing about the first milestone, which is those solar arrays coming out. So
thank you, George.
Dave, thank you very much.
All right.
And we're at T-minus 1 hour, 50 minutes, 5 seconds and counting. This is Atlas Launch Control.
1 hour, 50 minutes. Sorry.
CFA purge and displacement mode.
Roger.
Com check on countdown net 1, NSC,
Loud and clear.
NLM, SMD, DSMD,
LCRC1.
Go ahead, RC.
Be advised, I have no range safety closures for today's operation.
Roger. NLM Channel 1. NSC,
NLM.
Roger, NLM. Performing a comm check on Countdown Net 1. NLM, LC.
LC, this is NLM. I have you 5 by how me?
Roger, have you loud and clear. SMD, LC.
Go ahead. This is SMD.
Roger, SMD. Performing a comm check on Countdown Net 1.
Copy that. Loud and clear.
Roger. DSMD.
5 by. DSMD is 5 by.
I copy.
Step 270. CEC safety purge is active.
Roger.
CEP on high flow.
Roger.
Centaur LO2 transfer line chill down complete.
Roger. Start Centaur LO2 tanking.
Roger.
Perform Centaur LH2 SVV cycle test.
Roger.
need to go down there. This is Atlas Launch Control, T-minus 1 hour, 42 minutes, 51 seconds and counting. Joining us now here in the Atlas Spaceflight Operations Center is Jim Morrissey, the Instrument Systems Manager for MAVEN from NASA's Goddard Space Flight Center. And Jim, you've kind of been the technical man on these instruments to help get them ready to fly. Tell us quickly, how many instruments are on the spacecraft?
Well, we have 8 instruments plus a separate payload, which is our electrotransmitter. I think we'll be seeing a slide of all the payloads in a little bit.
All right, well, let's go ahead and roll the video, and Jim can tell us what we're seeing.
Okay, this is the MAVEN spacecraft. You can see there's the solar rays there. We have the solar wind analyzer and the solar wind electron analyzer. These are 2 instruments from California, Berkeley. There's the articulated payload platform that has 3 of our instruments that the platform allows to move as we pass through the atmosphere, so they can take samples of the atmosphere. And there's here's the spacecraft showing all the instruments. We have 2 different suites of instruments. Some of the, as I said, some of the instruments that are on the articulated payload platform, they sample the atmosphere as we travel, as we orbit the planet. And then we have a large number of instruments that are pointed in the same direction as the sun on the top panel where our solar rays are. And that's so that we can measure the solar energy as we take measurements of the composition of the atmosphere and correlate those 2 measurements throughout the mission.
Now, let's see, if I understood, there's like 8 instruments, but 9 sensors. Is that there's an additional sensor, or is it part of any of the others?
Right. One of our instruments is composed of 2 different components. So we count that as a single instrument, and that's our LPW, but it also has the EUV instrument is also part of that, the LPW package.
All right. Well, you've been with the all the operations to get the spacecraft instruments ready to fly on the spacecraft, tested and checked out. And so, and how much of that did you do after you got here to Kennedy Space Center?
Well, we after we got here, well, when we arrived here with the spacecraft, we had a few of our instruments had been sent back to, as planned, to the University of California, Berkeley, for some additional calibrations and retest after we did environmental testing in Denver. So we had to, we brought those back and we installed them back on the spacecraft. We also had an instrument that we brought back to Goddard for some additional testing and work, and that over a 2-week period, we had that back at Goddard for a while, and then we brought it back to the spacecraft. That was the NGIMS instrument.
Well, we've got some additional footage here. This is a little unique. We have some time-lapse footage of the MAVEN spacecraft and what we did to get it ready to fly. So tell us what we're seeing.
Yeah, so this is really new. This is footage that KSC takes for us, and the time-lapse footage you can see here. We're on the spacecraft is mounted on a mechanical fixture that allows us to rotate the spacecraft horizontally and vertically, and then spin it so that we're able to access all the different places we need to on the spacecraft as we go forward. So as Dave showed you earlier, we arrive with the solar rays on, but then we take them off to do testing, and then we bring them back. So you can sort of see that happening here. And then we rotate around, and we get into each of those bays, and there's a lot of blanketing, and here you can see. We with all our instruments, we do alignments on all the instruments to make sure they're pointing in exactly the direction we want them to be pointed in. And you can sort of see that happening now with the people on the obviously with the thing that looks like a camera there. And then let's see later on. As we're in here, there's still a lot of things that we need to do once we get to the processing facility. Mostly blanketing, and you won't see this here, but we also, when we arrive, we don't have any fuel in us, so we have to do a full propellant loading and load up the tanks. You can see here the lights are on, so they're doing a test of the solar rays, making sure that those are connected properly. And here you can see the preparations for spin balance. where we spin the spacecraft. That's the fixture on the right, and then you could see on the left, and then here you see the fairing that United Launch Alliance provides, and they bring that in, and here we are getting ready, and then you can see we're about to be encapsulated, and this is the last time we get to see the spacecraft and work on it. So there it's all closed up, and I think in a second, a little bit of a delay, and then you're going to see the guys. Those are the United Launch Alliance guys installing the pyrotechnics and the things along the seams of the fairing that allow it to separate once we're off the pad. So that fairing will be opening up later on today as we're launching and exposing the spacecraft just prior to separation from the launch vehicle.
So at that point, you're finished and ready to roll out.
Right. That's the end of the video. Yeah.
Now what? When's the first time these instruments we're discussing are going to come on, and you'll be able to see if they're working?
We'll be turning them on, not right away, because there's other critical elements of the spacecraft that we would need to make sure are functioning. But it'll be in about 2 weeks, 2 or 3 weeks. We'll do it over a 2-week period and just go through all the instruments and check out their health and safety and make sure they're operating the way we think they should be.
All right, Jim. Well, thank you very much.
Thank you, George.
We're certainly looking forward to, once you get to Mars, to hearing about the instruments, because we've had a lot of discussion about their capabilities. So that's certainly what this is all about. Thank you very much.
Right. Thank you, George.
Jim. We're at T-minus 1 hour, 36 minutes, 21 seconds and counting. This is Atlas Launch Control.
Centaur LO2 at 30%.
Roger.
Step 410, Centaur bottles of flight mass.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 30 minutes, 45 seconds and counting. Just momentarily, we are going to be hearing the start of the liquid oxygen tanking.
Step 370, CFA purge has been in displacement mode for over 25 minutes.
Roger.
T-minus 1 hour, 30 minutes.
Centaur LO2 at 50%.
Roger.
RP1 pressure decay test complete, and RP1 tank is stable at step 2 pressure.
Roger.
ECB stable at prefill.
Roger.
RD-180 has been on heated GN2 for 20 minutes minimum.
Roger.
Atlas LO2 ground chill down is complete.
Roger. Start Atlas LO2 tanking operations.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 28 minutes and 55 seconds and counting. Just started tanking liquid oxygen aboard the Atlas booster stage. And joining us now in the Mission Director Center at the Atlas Space Flight Operations Center is Chuck Tatro. He is the MAVEN Mission Manager for Kennedy Space Center's Launch Services Program. And Chuck, I believe your primary responsibility is sort of the trying to integrate the Atlas and the MAVEN spacecraft together. You're kind of the person that makes this match work. Is that correct?
Yes, I lead a team from the Launch Services Program that works to not only procure the launch vehicle from United Launch Alliance, but also manage the integration and the interfaces between the spacecraft and the launch vehicle, so that the launch vehicle and the spacecraft meet together and work together for a successful launch.
So you've been working with the vehicle team for some time. We've got some video now that kind of goes back to when the Atlas and Centaur stages arrived at Port Canaveral. If we could go ahead and roll that video, and Chuck, tell us what we're seeing for the rest of the flow.
All right. Well, the Atlas booster and Centaur arrived from Decatur, Alabama on the Delta Mariner. It's a specially designed transport ship that brings the vehicle segments down from Alabama. The only thing that does not come on the Mariner is the launch vehicle fairing, which is manufactured in Harlingen, Texas. So these this is the launch vehicle, the Atlas, and this is the Centaur here, coming out of the Delta Mariner early in the morning on the 26th of August, headed for a convoy to the Atlas Space Operations Center here, where we are today, for horizontal testing and integration. This is the first time when the launch vehicle booster, the Atlas, and the Centaur are connected electronically to make sure that they can talk to each other and simulate some of the flight environments for them. So they're tested horizontally before they're brought out to the vertical integration facility. As we see here, they're backing the Atlas into the horizontal bay and getting ready. Here's the Centaur being moved into that position, so that they can actually do that. Then we have a couple of simulant pictures here. Since the government furlough was in place, we didn't get active video of the erection of MAVEN's vehicle. Here's the fairing encapsulation in the payload hazardous servicing facility at Kennedy Space Center. The fairing halves go together. This, as I said, this fairing is manufactured in Harlingen, Texas, and the MAVEN logo is painted on by a special paint crew there in Harlingen. They did a fantastic job. This encapsulated spacecraft is being rolled into the airlock for getting ready for transport on the transportation container, and then arrival for a movement out to the vertical integration facility. It actually happened early on August 8th for MAVEN. So this is backing the trailer into the PHSF airlock so that the MAVEN could be stacked on board. Here you see MAVEN encapsulated fairing stacked on top of the truck and ready to go out to the vertical integration facility on the morning of August 8th. We like to transport late at night. There's no traffic on the roads. It's a good environmental time. It's quiet. The temperatures are usually the lowest, so it's generally when we like to do this operation. Here it is. You can see going past the OSB building out in the LC39 area. Here it is going past the shuttle vehicle assembly building on its way to Complex 41 VIF. Here it's arriving at the VIF. It arrived early in the morning, around 3:30 in the morning, and we just sat and waited for daylight. The operation was moved about an hour earlier than normal so we could avoid some higher winds that were scheduled to occur later in that morning. Here it is, you can see getting ready to lift. It's first light around 7 a.m. in the morning, and the encapsulated spacecraft is being lifted here on top of the already stacked Atlas and Centaur, which were already in place in the vertical integration facility. Here it is. This operation takes almost a full day for the team to carefully set the encapsulated payload and fairing down onto the rocket.
Well, Chuck, I know for our team here at Kennedy, we also have a team here that is going to be capturing a lot of the data when it comes back after launch. And can you tell us where all of that actually occurs?
We have a really extensive engineering and data team that are located back in Hangar AE, which we have 3 launch vehicle data centers, as well as a fully electronic and digitized telemetry laboratory where all of the streams of telemetry data for the vehicle and also for the spacecraft are brought back and analyzed, and they can be also recorded and looked at a later time. So we have a whole team back there in Hangar AE today that's supporting this mission.
Well, Chuck, thank you very much. And
my pleasure, George.
Very much looking forward now to see the next phase of getting ready for flight, and that's the launch.
We're all excited. Thanks, George.
At T-minus 1 hour, 23 minutes, 53 seconds, and counting, this is Atlas Launch Control.
Centaur LO2 at 80%.
Roger.
Centaur LO2 at 90%.
Roger.
LCRC-1.
Go ahead.
Be advised at this time range is is proceeding with the exception of Weather Rule 1 Bravo. Field Mill Rule had one site toggle off about 1 mile south of Complex 41. It's timing out. Should have a clear time of 17:05 Zulu.
Roger.
T-minus 1 hour, 20 minutes.
AHBs at flight pressure.
Roger.
Step 420, Atlas LO2 airborne chill down and slow fill complete. Fast fill started.
Roger.
Centaur LO2 at 96.4%. Topping started.
Roger.
Atlas LO2 at 10%.
Roger.
T-minus 1 hour, 17 minutes.
This is Atlas Launch Control, T-minus 1 hour, 16 minutes, 13 seconds, and counting. The launch window today is 2 hours in duration, extending from 1:28 to 3:28 p.m. Eastern Time. MAVEN has a 20-day nominal launch period with a daily launch window of 2 hours. Recent Mars missions have supplied conclusive evidence of flowing water on Mars millions of years ago. Surface features, imaged from orbit by cameras from such spacecraft as the Mars Reconnaissance Orbiter, show river networks, large basins, and glacier formations. Rovers such as Curiosity and Opportunity continue to collect geological evidence of ancient water, notably small-scale ripples preserved in rock formations and minerals that could have formed only in the presence of water. The Mars atmosphere is too thin and the temperatures too cold and dry. Surface water would either evaporate or freeze, since the temperatures average minus 64 degrees at the surface of Mars. Liquid water requires a thicker atmosphere and warmer climate. Discovering the fate of Mars water may depend on determining the fate of its atmosphere, and that is something that Principal Investigator Bruce Tchaikovsky will be discussing with us here in just a few minutes. All of our countdown operations continue on schedule. We're not working any issues either with the spacecraft or the Atlas V, and we're now at T-minus 1 hour, 14 minutes, 46 seconds and counting. This is Atlas Launch Control.
Atlas LO2 at 20%.
Roger.
CLO2 at flight level.
Roger.
LCRC1.
Go ahead, RC.
That field millet toggle off scale high is clear at this time. Range is proceeding.
Roger.
T-minus 1 hour, 10 minutes.
Atlas LO2 at 30%.
Roger.
CISA ECS set point has been reset for 15 minutes minimum.
Roger. Initiate Centaur engine chill down.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 9 minutes, 12 seconds and counting. Our countdown activities continue to run on schedule for 1:28 p.m. liftoff this afternoon. Joining us now is Vern Thorpe, the program manager from United Launch Alliance for our NASA missions. And Vern is going to talk to us some about the flight of the Atlas after it lifts off today, as well as discussing some of the things that are very special about this flight for United Launch Alliance and the community in Colorado and around Denver. So, first of all, let's go with the animation and tell us what we're seeing as the rocket lifts off.
Sure, George. This tape that you're about to see will give you a preview of what we expect to see later today. We're going to use an Atlas V vehicle to launch MAVEN. We're going to use our 401 configuration. It's a pretty big rocket, but it's actually our smallest Atlas V. You see liftoff there of the same configuration that we're using today. And since we have no solid strap-on rocket boosters, the first major event that you'll see after liftoff is when we've used up all the propellants in the booster tank and we shut down the booster engines and then separate that first stage from the rest of the vehicle. We will almost be in orbit at that time. There you see the engines shutting down. We'll activate a separation system and then fire some retro rockets to back that stage away from the rest of the vehicle. We then begin preparing for the first of 2 burns of the Centaur upper stage. And there you see our first engine burn. That first engine burn will last about 9.5 minutes. And 8 seconds into that burn, we'll jettison the payload fairing once we're above the atmosphere. Following that first 9.5 minute engine burn, we'll enter a coast phase. And if we launch at the beginning of the window, that coast phase will be 25 minutes long. After that, we'll be in position for our second burn, so we'll light the Centaur engine again, this time for about 5.5 minutes. And at the end of that burn, MAVEN will be on its way to Mars. And we'll do a few maneuvers to orient the spacecraft the way it needs to be. And then we'll separate it, begin a series of maneuvers with the Centaur upper stage to back it away from the spacecraft, and also adjust the trajectory enough so that there's no chance that it would ever impact Mars itself. So if we launch at the beginning of the window, it'll take a little less than an hour, about 52 minutes, to go from liftoff to spacecraft separation. If we have to move into the window for weather or for whatever other reason, the timeline could be extended up to 18 minutes.
Now, after the Centaur stops burning, I think you kind of indicated that there's actually a space in there of time between when the cutoff occurs and when the spacecraft separates. Is that right?
Yes, we're going to wait about 6 minutes to separate the spacecraft, and that's just 2 or 3 minutes longer than we usually wait, and that's just to make sure we've achieved all the pointing requirements and everything else that the spacecraft needs.
Well, Vern, this mission, this launch is a little unusual in what you could sort of call the Colorado connection. Could you tell us a little bit about why this is significant to Colorado?
Sure, I'd be happy to. Yeah, I mean, every time we launch one of these missions for NASA, it's kind of a showcase of what our country can do. But this mission really has a special meaning for Colorado. There's a lot of Colorado folks involved. I'm from Colorado myself. The science team that's behind this entire mission, led by Dr. Bruce Joukowsky, is from the University of Colorado up in Boulder. The spacecraft is built by Lockheed Martin in Colorado, and it will be operated by Lockheed Martin as well. And then, of course, United Launch Alliance, who I'm with, is headquartered in Colorado. So there's a very large number of Colorado organizations and Colorado people who are involved in this launch. And there's one other Colorado connection that I'd like to mention. We recently lost a great Coloradan who was also a pioneering member of the human spaceflight community. Scott Carpenter was born in Boulder, Colorado, and he passed away last month at the age of 88. And Scott was one of the original Mercury astronauts, and he actually flew to orbit on an Atlas rocket, predecessor of the vehicle you see here today. He was launched aboard an Atlas on May 24th in 1962 as cheering crowds lined the local beaches, and his flight was the second American manned orbital mission. He followed in the footsteps of John Glenn. Carpenter piloted his spacecraft through 3 orbits over a period of about 5 hours, and his goal was to demonstrate that humans could actually function and do work in a zero-G space environment. And when his mission was complete, he splashed down about 1,000 miles southeast of here, southeast of Cape Canaveral. His flight was obviously very successful for both himself, the Mercury program, for the Atlas vehicle, and it really helped lay a foundation for NASA space exploration. He and his fellow Mercury astronauts paved the way for NASA's march to the moon that led to the first lunar landing just 7 years after that. And over the years, Scott continued to be involved in the space community. He returned to KSC, the Kennedy Space Center, frequently to participate in various events, and he was here just last year for the 50th anniversary of Americans in Space. So in addition to launching MAVEN today, we're also taking time to remember and salute Mercury astronaut Scott Carpenter for his contribution to NASA's mission of space exploration.
Well, Vern, thanks very much. And it's kind of an interesting set of things that come together for this mission for Colorado, and the recognition of Scott Carpenter because he played such a significant role in the history of the manned space program for NASA.
Hey, thank you, George.
Thank you very much. And we're at T-minus 1 hour, 3 minutes, and counting. This is Atlas Launch Control.
Atlas LO2 at 50%.
Roger.
T-minus 60 minutes.
LH2 chill down complete.
Roger.
HB's at flight mass.
Roger. Start LH2 tanking.
Roger.
Adjust TEM ECS temperature per TRD.
Roger.
LCRC1.
Go ahead.
At this time, range is proceeding with the exception of Field Mill Rule 1 Bravo. Had another site kick over 1,000 volts, 2 nautical miles south of the pad. Estimated clear time 17:32 Zulu.
Roger.
Step 510, Atlas LO2 at 60%.
Roger. Initiate BRC ECS.
Roger.
T-minus 55 minutes.
Start flight control, final preps.
Roger.
This is Atlas Launch Control, T-minus 53 minutes, 56 seconds, and counting. We're joined now here in the Atlas Spaceflight Operations Center by Bruce Joukowsky. He is the MAVEN Principal Investigator for the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Bruce, welcome, and I think I'd like to begin by asking you, it's been sort of interesting to listen to some of your conversation occasionally about the evolution of how this mission started almost 10 years ago on the back of a napkin.
It has been 10 years since we started this, and the original discussion was between me and two members of what became the science team of did we think that this science was competitive in the proposal environment, and did we think we could pitch it in a way that would win the competition, and where did we think we would stand in terms of how important this science would stack up against others. We did decide to go ahead with a proposal, and the colleagues I was talking with and I became the center part of the science team.
Well, then, as we went along, how does NASA go about a competition and awarding a particular proposal such as yours?
In this case, they had announced that there would be a competition to propose a mission, and all comers could put in proposals. We put together a team, put together a proposal that included the science, the instruments, the spacecraft provider, the management, the operations, everything involved. 20 proposals were submitted, and NASA selected 2 for further study, and after a year of further competition, they selected us to go forward with development for flight.
Well, let's go now to some of the science, because I know that one point that you've made fairly consistently is that in the big picture, the science involved with this mission has something to do with the habitability of Mars. Is that right?
That's right, and that's one of the questions we think is important for understanding Mars, looking at the history of the climate and the atmosphere. If we look at some of the data that has come back from previous missions, we see a lot of evidence for liquid water having flowed over the surface in ancient times. We see river channels, features that look like there had been lakes inside of impact craters. Other features, similar geological features, we see minerals that form only in the presence of liquid water. All of these suggest that there had been water on the planet early in time, and today, of course, we see a cold, dry, desert-like planet. If we want to understand what happened, what caused that change, we need to understand where the water went, where the carbon dioxide from a thick early atmosphere that supported the higher temperatures would have gone. And that's really what's driving us. By understanding the history of water, we understand both the history of the geology of the surface and the history of the habitability by microbes. Water is a requirement for life, and if we understand where the water has been and why it's not there anymore, we can learn more about what the history of the potential for life has been.
So how do we tie that into the atmosphere and the upper atmosphere?
Well, if you ask where did the water go, where did the CO2 go, it can go down into the subsurface. The CO2 can form carbon-bearing minerals, for example, but we don't see evidence for that. not in enough abundance to account for for as much CO2 as would have to have been there. Instead, the other place it can go, the gases can go to the top of the atmosphere and be stripped away to space. The sun, the solar wind, they can drive processes that remove gas from the top of the atmosphere, and that's what we'll be studying. We want to understand whether the sun was able to remove gas from the top of the atmosphere and how much. If we can go to the first graphic here, this is a cartoon sketch showing the different processes that we think may have operated early in Mars history. I'm not going to walk through this. It would take a long time and bore everybody. But we designed the mission to understand each of these processes, starting with the sun input from the upper left, the solar wind, the extreme ultraviolet light, solar storm events, and then how they can drive different processes in the atmosphere. We selected the instruments to be able to look at each one of these processes and see how they operate today and understand how they could have operated in the past. What I'd like to do is go through just one of those processes and give you an example of how it works, and that's the stripping by the solar wind. As the solar wind goes by, it can grab ions and remove them from the atmosphere. We have a simulation coming up in just a second here that will show a computer simulation of how that stripping process works. Here we're seeing the planet. The colors represent the upper atmosphere. The arrows represent the solar wind going by. And you can see that the gas is just being picked up and streamed away. This is a very tenuous part of the upper atmosphere, so we're not talking about a lot of gas, and it's a very slow leakage rate, if you will. But early in history, when the solar wind was more intense, when the solar ultraviolet was more intense, we think that the escape rates would have been greater. So by looking now and seeing processes like this, we think we can understand what happened 4 billion years ago.
Well, Bruce, where will your team actually be when they first see some of this science coming in?
We have a distributed science team, and some of the members will be at the University of Colorado, where I'm stationed, at University of California, Berkeley, at Goddard Space Flight Center, and at several other institutions around the country and a couple abroad as well.
And you expect to start seeing some of that science when for the first time?
We go into orbit in late September of next year. It takes us about 5 weeks to commission the spacecraft to get ready to do the observations, and then we'll start to get the measurements. I'm thinking that it will take us about 3 months to be sure we understand how the instruments are working, make sure they're calibrated properly, and we can begin to understand what the data are telling us. So I think we're looking at beginning to have some of our key science results starting early in 2015, about 14 months from now.
Well, Bruce, thank you very much, and sure your team has with so much effort over the years to put this mission together. This is coming to a pinnacle, an apex here in just less than an hour.
This is incredibly exciting, and you're sitting here with the same view that I've got of the rocket on the pad up on the screen here, and we're just excited right now and hoping for the best.
Bruce, thanks very much.
Thank you.
And we're at T-minus 46 minutes, 7 seconds and counting. This is Atlas Launch Control.
LH2 70%.
Roger.
LH2 at 80%.
Roger.
T-minus 43 minutes.
Atlas LO2 at 90%.
Roger.
LH2 at 90%.
Roger.
T-minus 42 minutes.
ECB at flight pressure.
Roger.
LC, RCN1.
Go ahead.
Roger that. I was reporting that we are now green on all weather constraints. Range is green.
Roger.
T-minus 40 minutes.
Start final open loop FTS test. Roger.
Step 570, Atlas LO2 at 97.5%, topping started.
Roger. All steps are complete through step number 590.
Step 620, Centaur LH2 at 96.2%, topping started.
Roger. Perform Centaur LH2 fill and drain valve cycle test.
Roger.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
Centaur LO2 fill and drain valve cycle test is complete.
Roger.
Step 630, Centaur LH2 fill and drain valve cycle test complete.
Roger. Perform Centaur SRV and LH2 SVV cycling test.
Roger.
This is Atlas Launch Control, T-minus 35 minutes, 25 seconds, and counting. As we've heard, we've completed the cycling of our fill and drain valves on the Atlas and Centaur, and we are continuing without any issues on the vehicle whatsoever. We have some additional tests coming up we've got a fill and drain valve test on the Atlas test right now, and a functional test. See the Coast Guard offshore there patrolling the waterways and security, NASA security. Right now, the only thing going on is our launch weather officer, Clay Flynn, reports that some of the field mills, which measure the electrical potential in the area, are beginning to toggle back and forth between the acceptable limits and are being watched with some indication that there is a cirrus anvil cloud overhead that makes those field mills at time go out of specification. But right now all the field mills are green. But that's something that may happen as we have some clouds begin to move into the area. The field mills that measure electrical potential could go in and out of limits. So at the moment we had one go out, and now it's back in, and at the moment we're green. But that could continue to happen about any time through the balance of the count and into the launch window, as long as we have some cloudiness approaching us from the northwest. Otherwise, we're continuing with our fill and drain valve cycling. We've completed the first round of that and going into concluding that activity, which will keep us completely on schedule for a 1:28 p.m. liftoff. At T-minus 33 minutes, 16 seconds and counting, this is Atlas Launch Control.
Are complete.
Roger. Resume Centaur LH2 topping to flight level.
Roger.
Resume Centaur LO2 topping to flight level.
Roger.
LC Redline Monitor.
Go ahead, Redline Monitor.
Yes, LC at T-minus 43:15 approximately. Redline Monitor indicated an OTC on measurement Charlie Uniform Kilo 020 Echo. That is a Centaur liquid oxygen delta pressure measurement.
Roger. Centaur Pneumatics, LC.
This Centaur Pneumatics.
Roger. You observing any problems with tank pressures? Or did we maybe pick something up during the vent valve test?
I don't see anything out of the ordinary. The Centaur vent valve cycle test seemed to be nominal. What was the measurement again?
Charlie Uniform Kilo 020 Echo. Okay. Tank pressures at this time are indicating nominally?
Tank pressures at this time are indicating nominally, correct.
Roger. AC, LC, channel 1.
ACN1.
Roger. Redline Monitor reported a OTC violation on Charlie Uniform Kilo 020 Echo, Centaur LH2 Delta P measurement. Please convene the anomaly team and provide a recommendation.
Roger.
T-minus 31 minutes.
LC is Redline Monitor.
Go ahead.
Yeah, we've been reading in band on that measurement Charlie Uniform Kilo 020 Echo for some time now. Could we go ahead and reset that violation, acknowledge that?
Roger, reset it at this time.
Roger, in work.
This is Atlas Launch Control, T-minus 25 minutes 45 seconds and counting. Today's launch is dedicated in memory of Grover Hall and Adam Crocker. In his 39-year career, Adam Hall with Lockheed Martin Space Systems and also Adam Crocker held a number of key engineering management positions, including a vice president of NASA Systems, overseeing Magellan, tethered satellite, and flight telebotics resurfacer. Adam Crocker was a student at Colorado State University, an Air Force ROTC cadet, a pilot, and a young man interested in space. His father, sister, and brother-in-law are members of the spaceflight community at Lockheed Martin and United Launch Alliance, who have all been involved with the MAVEN mission and the Atlas program. So again, our dedication of this launch to Grover Hall and Adam Crocker.
LC, step 810, FTS open loop test is complete.
Roger.
LC, ALO.
Go ahead.
Step 640, Atlas LO2, fill and drain valve cycle test complete.
Roger.
Atlas airborne vent valve functional test is complete.
Roger. Perform pogo suppressor charge.
Roger.
This is Atlas Launch Control, T-minus 21 minutes, 33 seconds, and counting. The Atlas V rocket has two stages. The Atlas booster stage is 106.5 feet long, 12.5 feet in diameter, and it burns two propellants. RP1, which is a highly refined kerosene. There's approximately 26,000 gallons on board. And liquid oxygen. There is approximately 50,000 gallons loaded on board the Atlas. The Centaur stage is 41.5 feet long, 10 feet in diameter, and it burns liquid hydrogen and liquid oxygen through its RL-10 engines. There's approximately 12,000 gallons of hydrogen loaded aboard now, the Centaur stage, and 4,000 gallons of liquid oxygen. The height of the vehicle on the pad is 191 feet. And it will weigh approximately 750,000 pounds at liftoff. Right now we're not working any issues. The field mills currently are green, and they may drift in and out occasionally with the encroachment of some cloudiness from the northwest. And the one other indication that we were working was associated with our fill and drain valves is apparently a transducer issue and does not appear to be a concern. So we're at T-minus 19 minutes, 33 seconds and counting. This is Atlas Launch Control.
LC, ALO.
Go ahead.
Step 690, pogo suppressor charge complete.
Roger.
T-minus 19 minutes.
LC Flight Control Channel 1.
Go ahead, Flight Control.
Step 750 BRC SIB1 and SIB2 voltage checks are complete.
Roger, LD. NLM, Channel 1.
NLM's on.
Roger.
LC, AC on 1.
Go ahead.
Roger, sir. I'm ready to provide the outbrief for the red line monitor issue.
Proceed.
Roger, sir. The team has reviewed the data associated with measurement Charlie Uniform Kilo 020 Echo, and the transducer is indeed reading a little high to family, but it's within spec. There is no concern with proceeding through the rest of the count and flight. We should not see a recurrence of this issue with any planned operations. Recommendation is to proceed.
Roger. Copy and concur. NLM?
NLM copies and concurs.
And LD?
LD concurs.
RD-180 transducer converter calibration is complete.
Roger. RC, conduct weather briefing on Channel 8 Weather Conference Net.
Roger. LWO, Range Coordinator, Channel 8.
LWO.
Please stand by for final weather brief.
Standing by.
Following personnel acknowledge standing by for the weather brief. NLM.
NLM.
LD.
LD.
AFLD.
AFLD.
LWO, please proceed with your brief.
Yes, sir. This is LWO for the L-30 weather brief on Weather Brief CC Local and Channel 8. You should have a satellite picture of the peninsula of Florida on your CCTV monitor at this time. You'll know the blue quarter there is the amble cloud tool. We continue to have amble cloud streaming over the pad. It is below criteria, so we are go and view that as a low threat of violating any amble cloud criteria during the beginning of the window, more so towards mid to latter part of the window. Likewise, there are cumulus clouds in the vicinity. Let me go ahead to the radar. There are some cumulus clouds embedded in that anomalous propagation that you see, those light blues that you see over the Cape and south of the Cape. However, the peak, we have the one in the area, the tops of all those clouds are topping out at about 8,000 feet. It would only be a fly-through constraint if it was up to about 12,700 feet. So it looks like at this time, although they should continue to build at this time, there's not a threat for we're not violating cumulus cloud rule violation. However, the more heat we get and the closer the front gets here, we'll have a greater threat during the mid to latter part of the window. Still a potential, but at this time all LCCs are go and expected to remain go during the beginning of the window. Taking a look at the the winds out of complex 41. Winds still relatively light, gusting to about 7 knots. They shouldn't gain much more. I'm going 10 gust 15, which perhaps is a little bit high. In terms of the direction, they're still out of the northeast. I think eventually they'll become southeast, but nevertheless out of the east and staying under 15 knots for peak gust. In terms of the temperature at the present time, we're in the about 78 degrees, and we'll bounce around 78 to 80 on that order. In terms of the upper level profile, the winds did drop off a good little bit between 20 and 25,000 feet. Looks like almost 20 knots in this range. Don't expect to see a great change in drop off of the profile for the balance of the count window. In terms of the ops forecast, looking for multiple cloud layers, 7 miles of visibility, winds from the east, all out of the easterly direction, 10 gusting to 15. We should see isolated showers during the window, but the front end of the window certainly looks better. Temperature in the 79 to 82 range with a 40% chance of violation. All LCCs are go at this time. There's no change in the 24-hour, no change in the 48-hour. In terms of proton flux, it remains at normal background levels. And in terms of the exposure, low threat of any type of lightning, not expecting any type of lightning in the next hour to two, and then a small threat after 2 o'clock with the greatest threat after 1400 or 1600 local. This concludes the weather brief. Pending your questions, sir.
Range coordinator has no questions.
LD here, one question. What time of the count do you stop latest you'd call a field mill by?
I'm sorry, sir. I couldn't hear your question.
When is the last point you would call a field mill violation in our per CONOP?
Sir, the last time we'll get a field mill update is 1 minute out from T0. They update a few seconds after the top of the hour, so it would be probably 50 seconds. 50 seconds, at not later than 50 seconds after 1 minute prior to T0.
Roger that. Thank you.
Yes, sir.
FLD, no questions.
NLM, no questions.
This is Atlas Launch Control, T-minus 13 minutes, 16 seconds and counting. We have a hold coming up at T-minus 4 minutes. That is a 10-minute hold. And as you heard, the weather briefing right now, the weather is go, and our one technical issue has been cleared. So we're continuing to press on to a launch at 1:28 p.m. At T-minus 12 minutes, 50 seconds and counting. This is Atlas Launch Control.
LCFC Channel 1.
Go ahead.
Step 800, the primary address text hex file, address _ alpha victor 038 _ 05 with SDL CRC of 0 echo 1 Bravo has been received, verified, and is ready to load into the FTINU.
Proceed with load.
Copy.
T-minus 11 minutes. T-minus 10 minutes.
This is Atlas Launch Control, T-minus 9 minutes and counting. Headed down to hold at T-minus 4 minutes, which is 10 minutes in duration. At this time, the launch vehicle is green, the range is green, and the MAVEN spacecraft is green. MAVEN at launch will weigh 5,421 pounds. It has 2,000 solar cells on its 4 solar array panels. They generate between 1,150 watts and 1,700 watts, depending on the spacecraft's location above Mars. Once we get into our final hold at T-minus 4 minutes, we'll have the final polls from Omar Baez and the NASA launch team, and then the polling of the United Launch Alliance launch team. But at this time, we continue to press toward a launch at 1:28 p.m. This is Atlas Launch Control, T-minus 7 minutes, 50 seconds, and counting.
Step 830, primary address tech hex file address underscore alpha vector 038 underscore 05 with SDLCRC of 0 Echo 1 Bravo has been loaded into the FTINU and verified.
Roger. All steps are complete through step number 850.
T-minus 6 minutes.
Fuel fill sequence is complete.
Roger.
This is Atlas Launch Control, T-minus 5 minutes 15 seconds and counting. Once we lift off from the pad, the Air Force tracking stations here at the Cape will be supplying the data, and supplemented by the South Florida data from Jupiter Inlet at about a minute 14 into the count.
Roger.
Then the Antigua station will provide coverage until acquisition through Tidris East, about 13 minutes into the flight. Standing by to go into the planned built-in hold at 4 minutes. Going into the hold in 5, 4, 3, 2, 1. T-minus 4 minutes.
T-minus 4
and
minutes
holding.
This is a program 10-minute hold.
Verify the FCO, RCO, and OSM hold fire switches are in the proceed position.
Ready to proceed.
DTP status verified.
Roger.
This is the NLM on the NLM net with our final launch readiness poll to release the hold at T-minus 4 minutes. NASA CE.
NASA CE, go.
SMA.
SMA is go.
SMD.
SMD is go for final count.
NASA Mission Manager.
Mission management is go, Omar.
NAM.
NAM is ready.
Copy that. The NASA team is ready for launch.
Perform launch on time verification.
Roger.
Now we're going to astronaut Michael Hall aboard the International Space Station, launched on the ISS on September 25th, 2013.
Greetings from the International Space Station. I'm NASA Flight Engineer Mike Hopkins of the Expedition 38 crew. We want to wish the MAVEN team a successful flight to Mars. Like a lot of the research we're conducting on the International Space Station, understanding the red planet's atmosphere is essential to NASA's goal of safely sending humans there one day. From the International Space Station, best wishes for a fabulous mission.
And with best wishes from astronaut Michael Hopkins, we'll be standing by to come out of the planned built-in hold, not working any issues in the countdown. We'll have our launch conductor Doug LeBeau from United Launch Alliance polling his launch team.
LC flight control on 1.
Go ahead.
Launch on time verified.
Roger. Verify solar radiation acceptable for launch.
Verified.
Spacecraft to internal power.
Roger.
LC switch to ready position. All steps are complete prior to the status check.
Once we have liftoff, we'll be hearing United Launch Alliance Atlas V telemetry manager Rob Gannon providing the flight ascent calls for the Atlas as it moves into space. We'll get the final go for Atlas readiness and Centaur readiness at T-minus 25 seconds.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
Timer.
Go.
GCQ.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicles ready to launch.
Proceeding with the count. T0 is planned for 18:28 Zulu. Set count to start at 18:24 Zulu.
Roger. T0 is set for 18:28 Zulu. Count will start at 18:24 Zulu.
And we've just had a go for launch from MAVEN Spacecraft Mission Director and Project Manager David Mitchell. Once we're at T-minus 1 minute 55 seconds, the automatic sequencer will take over the automated control of the countdown from that point to liftoff. The RD-180 engines will ignite about 3.8 seconds before liftoff.
Spacecraft on internal power.
Roger. All steps are complete prior to terminal count.
Picking up the count in 30 seconds.
On my mark, time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting.
3:55.
Ground pyros enabled.
T-minus 3.5 minutes.
Three minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
250.
FTS internal.
T-minus 2 minutes 30 seconds.
Two minutes.
Vehicle power internal.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur LO2.
140.
Launch enabled.
FTS armed.
T-minus 90 seconds.
$120.
Orca's armed.
FCS count started.
$110.
Vent valves locked.
One minute.
Rock, report range status.
Range green.
Standing by for final Atlas and Centaur go.
40. Stable at step 3.
25.
Status check.
Go Atlas.
Go Centaur.
Go MAVEN.
20. 15.
T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, ignition, and liftoff of the Atlas V with MAVEN, looking for clues about the evolution of Mars through its atmosphere.
Control. Mark. Everything looking good. Still at 100% rated thrust on the RD-180. Vehicle rates are looking good. We do have roll program in, right as expected. We are actively controlling mixture ratio. Valve position looks good. Thrust regulator valve position looks good. Speeds are good. And vehicle's operating as expected. Continue down the center of the range track. Everything is looking good. We're now 1.6 nautical miles of altitude, 1.1 miles downrange, traveling at a little over 1,000 miles per hour. And we have ended our roll programs. Everything is looking good, continuing at 100% thrust. And we are now passing through the sound barrier. MAVEN is now supersonic. RD-180 continues to operate at 100% rated thrust. We are about to pass through max Q. And vehicles passing through max Q. Rates look good. Engine continues to operate at 100%, and we have throttled down to 95% thrust, right on time. And we're now 10 nautical miles in altitude, 7.4 miles downrange, traveling at 2,200 miles per hour. And everything is looking good. Continue to operate at 95% thrust. Coming up on our next mark event, I expect to enable Q-alpha steering. And steering's enabled. Body rates look as expected for bringing in steering. Vehicle is now 50% of its liftoff weight. And we're about to fire the pyro valves to activate the second stage reaction control system. Pyro valves have fired. System has pressurized. And the RD-180 continues to operate as expected at 100% rated thrust, or 95% rated thrust, correction. Rates are looking good. Continue to accelerate, passing through 3 Gs. PU control looks good. And continue to fly right down the center of the range track. We are now 35 miles in altitude, 70 miles downrange at 6,000 miles per hour. Reaction control system is now fully pressurized. And continuing to operate at 95%. Good PU control. Smooth body rates. Continue to have nominal acceleration. Vehicle is now 25% of its liftoff weight. We are now throttling the engine to actively control at 5 Gs. We have started boost phase chill down. Housing temps are reacting as expected. Continuing to operate the RD-180 as expected. We are now flying a 4.6 G throttle profile. Engine is throttling, getting ready for booster engine cutoff. We have BECO coming up on staging. We have stage separation. Everything is looking good. We have pre-start on fuel and locks. Everything's looking at ignition, full thrust. Centaur main engine is up at 100% rated thrust, coming up on fairing separation. We have fairing set. And rates look good for fairing separation. Should be cutting back in on closed loop control. And we've done purge firings in the reaction control system as expected. We do have closed loop control reestablished after fairing jettison. The RL-10 continues to operate as expected, nice and smooth. PU is in open loop control as expected. Axial acceleration is steady. We are now 93 or 107 miles in altitude, 426 miles downrange, traveling at 11,700 miles per hour. Vehicle is continuing right down the center of the range track. Everything looking good. We are seeing our expected thruster, reaction control thruster, thermal maintenance firings. Body rates are nice and smooth. Everything is continuing to look good. Engine operating parameters are good. We are now in the process of executing a 9-minute, 30-second first burn of Centaur. Everything is looking good. We have closed loop control on the PU system about a little over 20 seconds ago. That transition looks as expected. Continuing to operate at a LOX-rich mixture ratio. We have now begun our roll to TDRS attitude. Our delta PE for boost phase, or preliminary look, gives us 78 pounds of delta PE. That's 1 sigma high to our nominal rate. We had format change. And continuing to get clean data. Engines continue to operate as expected. Then we see our expected activity on the reaction control thrusters. 152 miles in altitude, 826 miles downrange, traveling at 12,500 miles per hour. And PU continues to operate on the lock stop. That's as expected for this time in flight. We are seeing some noise in telemetry at this time, but enough data is coming through. We're seeing steady operating pressure levels on the RL-10. Everything is looking good. And I continue to see the mass error signal correct itself as expected. Engine pressures are nice and smooth. Accelerating smoothly, a little over half a G at this time. And we're seeing all of our reaction control system temperatures come together as we condition the system. And everything looking good. And PU's continuing on the lock stop. Everything looking good. Here you see our expected thruster firings. Very little roll control has been needed. Passing through 9 minutes into the mission, everything looking good. RL-10 is operating nominally. Seeing smooth body rates.
Have loss of contact here at the Cape in communications. Antigua is now providing data.
Engine operating normally. Everything looking good. Steady acceleration at 0.56 Gs, right down the center of the range track. 168 miles in altitude, 1,400 miles downrange, traveling at 14,000 miles per hour. Everything is looking good. Operating parameters on the engine, very steady, nice and smooth. We are seeing oxidizer error in the PU system control coming towards nominal. The valve has come off the stop. Seeing active control of the PU valve now on the RL10. Vehicle continues to burn normally. And since we have launched at the beginning of the window, we are expecting our spacecraft separation time right at 52 minutes, 42 seconds into the mission. And continuing to see active control, Centaur PU. Engine pressures are reacting as expected to the change in mixture ratio. Smooth body rates. Nominal performance down the range track. We are inside of 3 minutes to MECO 1. PU controls coming up near the nominal mixture ratio. Engine continues to operate as expected, seeing the normal small adjustments in engine pressures as the PU valve slews. Our PU middle. Rates are good. Pressures are good. RCS activity is right as expected. Very little roll control is being required out of the reaction control system. Engine is burning normally. We are now inside of 2 minutes to MECO 1. MAVEN is continuing to fly normally. Once we complete this burn of Centaur, first burn of Centaur, we will enter a 27-minute, 36-second coast phase, followed by a second burn and then spacecraft separation. Continuing to look at very good telemetry data. Engine is good, rates are good. As noted before, seeing normal activity in the control system with very little roll control needed. PU is now operating near nominal mixture ratio. And everything is looking normal on the vehicle. And we're approaching 30 seconds to MECO 1. Coming up on MECO 1, vehicle's looking good. 10 seconds to a expected MECO 1 time. Open loop on PU, locked, and MECO. We have cutoff. Cutoff time right as expected. Everything looks good. 4S settling thrusters are on. And we are beginning to reorient to our PTC attitude and starting our PTC roll. And we are actively controlling pressure in the tank by controlling our vent valve locking. Everything looks good there. Now climbing into our PTC roll rate of 1.5 degrees per second, and we have now achieved that rate. Continuing to see settling as expected.
And our nominal orbit right now during the coast phase is 87 nautical miles by 170 nautical miles. Coming up, losing our data through Antigua and acquisition through the TDRS East tracking and data relay satellite.
Good bus voltages. Plenty of pressure in our Centaur helium bottle. Continuing to see our PTC roll. Very clean data. We're seeing minor dropouts as the vehicle's rolling as expected. But we recover and continue to see good data.
While we're in the coast phase, we're going to be looking at some launch replays from the ground.
And we have had a vent valve cycle. Center hydrogen tank, pressure's dropped as expected. Bus battery voltages look good, helium storage looks good. Vehicle's going to roll and reorient itself as expected. Very clean, active autopilot control. Can we see our expected reaction control system activity? And continuing with 4S settling. Next event we'll see is starting to ramp our settling down to a 12.5% duty cycle. It'll kick in approximately a little over 30 seconds from now. Currently have a telemetry dropout, and we've recovered telemetry. Continuing to see normal coast phase performance. And we've begun our ramping of Centaur settling down to a 12.5% duty cycle. Bus battery voltage is good. Helium storage looks good. Next event we're looking for is securing our C-band transponder. And we have secured the transponder within a couple seconds of nominal. And we've in the process of executing a PTC roll reversal. And we're now steadying out. telemetry dropout in progress now. Nothing unexpected for this time of flight. And we can see with the recovery of data that we have achieved our roll reversal. Now settled out at a minus 1.5 degree per second roll rate. And next mark of for approximately 6 minutes from now is our and our next mark event we are looking for is our duct flush on Centaur. It's just around 5 minutes from now. Vehicle continuing in normal coast phase. Pitch and yaw rates are steady, right around 0 degrees per second as expected, and we're at the minus 1.5 degree per second roll rate. Bus battery voltages are good. Tank pressures, helium storage pressure is looking good. And reaction control system activities as expected this time in flight. Okay, we're in the middle portion of our 27.5-minute coast phase. Continuing to look good. Centaur pressures and voltages are looking good. Rates are smooth, right as expected. As noted before, we will be executing a second burn of Centaur. Duration of that is 5.5 minutes. Following that, we will have a 5-minute, 49-second coast phase to a spacecraft separation, 52 minutes, 42 seconds mission elapsed time. Yeah, Centaur and MAVEN continue to coast nominally. Coming up on 1500 seconds. Mission elapsed time. Bus battery voltages look good. Reaction control system firings look good. Body rates look good. Everything looks normal. We're now 1 minute to our duct flush expected time. Vehicle parameters are normal. "30 seconds to the duct flush. And we're executing our duct flush. Everything looks good. Inlet pressure shows we have closed the valve. Sequence timing was as expected. Continue to see expected performance, good bus battery voltages, good tank and helium storage bottle pressures. Rates are smooth. Passing through 1650 seconds into the flight. Everything looks good. PTC roll continuing to be executed at -1.5 degrees per second. Settling duty cycle at 12.5%. Bus battery voltages are as expected, a little over 30 volts DC. Storage bottle pressures are good. And tank pressures are good. And we're now executing a roll reversal for our PTC. And here seeing the rates change. Coming through 0%, heading towards a positive 1.5 degree per second roll. Passing through 1.3 degrees per second, approaching our target. And we're settling out at a positive 1.5 degree per second PTC roll. And passing through 1,800 seconds into the mission, everything is looking good. Rates are steady with pitch and yaw at 0 as expected, and a positive 1.5 degree per second roll rate. Everything else is stable. We have no change for bus battery voltages, are right as expected. Same conclusion with storage bottle pressures for our helium system. And tank pressures look good as well. Passing through 1,900 seconds into the mission, everything continues to look good. No change from previous reports. All parameters are monitoring right as expected. Nice and smooth. And we just passed through 33 minutes into the mission. Everything is continuing to look good. And we're now seeing some active propellant conditioning in the Centaur LH2 tank. Vent valve cycles are bringing tank pressure down. And we're now at a 50% duty cycle on RCS settling. Fuel tank pressure steadied out right as expected. As before, bus battery voltages continue to look good. Tank pressures look good. And we're now in the process of turning to our MES-2 attitude. Vehicle sequence continues to be executed nominally. Seeing some changes in pitch and yaw rates as the vehicle reorients itself. Roll rate continues at our PTC roll rate. Just passed through 36 minutes in the mission. Everything continues to look good. We're now 5 minutes to MES-2. Passing through 37 minutes into the mission, the vehicle continues to change its pointing for MES-2 attitude with a positive 1.5 degree per second PTC roll. 50% settling is in progress as expected. We're actively controlling fuel tank pressures, conditioning the propellants. Thirty-eight minutes into the mission, everything looking good. And we are despinning our PTC roll as expected. We are now inside of 3 minutes to second burn. Our second burn sequence will begin with switching to 100% settling. We will then increase propellant tank pressures, followed by LH2 pre-start, 33 seconds prior to MES. And an LO2 pre-start sequence, it starts just under 18 seconds before MES. Two minutes to second burn. Vehicle continues to reorient itself to our second burn attitude. And we're about to start our pre-MES sequence. And we've begun our pre-mess sequence. We're at 100% settling. And we're now adjusting tank pressures, fuel tank pressure coming up. Everything's looking good for the second burn of Centaur. This will be a 5.5 minute nominal burn. Now 20 seconds to pre-start on LH2. Continuing to change our tank pressures as expected. And we have LH2 pre-start. PU valve is moving to its start position. Locks pre-start. Looking good, coming up on MES. Ignition, full thrust. Main engine is up to nominal operating parameters. Everything looks good. And we're seeing expected start transient is being nulled out in rates. Engine operating pressures are looking good. We are now in closed loop control on PU. We're correcting out a bit of a LOX bias. And now coming back up to a nominal mixture ratio. Seeing expected settling, we are executing a hydrazine burn-off sequence during the second burn to maximize vehicle performance. Engine pressures are looking good, rates are good. PU is controlling normally. And we're continuing to see expected reaction control system activity. Engine pressures are good, nice and smooth. PU control is very smooth. Just a little off nominal mixture ratio. Vehicle rates are nice and smooth. Everything looks good. And we're inside of 200 seconds to MECO 2. PU is now controlling nominal mixture ratio point. Engine pressures have been reacting to our changes in mixture ratio as expected. Engine operation is nice and smooth, good pressures. Vehicle rates are smooth. Mass air is smoothing out very nicely. Continuing to see expected reaction control system activity. Virtually no roll control appears to be needed. PU is continuing to control nominally. Now making a slight LOX correction. Engine pressures look good. Centaur continues to burn normally. Good engine pressures, good body rates. RCS activities right as expected. We are smoothly accelerating. 1.26 Gs. Good PU control. "100 seconds to MECO 2. Everything looking good, burning normally. Rate smooth, PU smooth, engine pressures steady at the appropriate levels. Inside of 1 minute to MECO 2. Following MECO 2, we'll have a 5-minute, 49-second coast duration to a spacecraft separation at 52 minutes, 42 seconds from liftoff. Everything looks good. 30 seconds to cut off. Inside of 20 seconds. Ten seconds to nominal cutoff time. Coming up on second main engine cutoff. And we have cutoff. Approximately 4 seconds long, well within our dispersions. Everything looks good. We are 4S settling. And vehicle rates are nulling out from the shutdown transient. Everything looks good. We are now executing our pre-spacecraft separation sequence. Everything looks good there. We are reorienting to our SEP attitude.
As mentioned, it'll be almost 6 minutes before spacecraft separation occurs.
Rates look good. Continuing to change our pointing for spacecraft SEP. For this mission, there is no spin-up required. All rates will be nulled for separation. We're now at a 50% duty cycle on reaction control system. We've unlocked the vent valve right on time. Venting the hydrogen tank. Pressure's coming down as expected. And everything looks good in this pre-spacecraft SEP sequence. Body rates are nulling out. Tank pressures look good, right where they're supposed to be. RCS activity is good. Continuing our expected sequence.
We're now 49 minutes, 10 seconds into the flight of the Atlas V with MAVEN. Spacecraft separation is at 52 minutes, 42 seconds.
Yeah, 3 minutes to spacecraft SEP. Everything looking good in this coast base coming up to spacecraft set. Vehicle sequencing continues to be as expected. Two minutes to spacecraft set. Everything looking good. And we're seeing our expected performance from the reaction control system. Body rates are now leveled at 0. We've apparently achieved our pointing for spacecraft set. One minute to spacecraft separation. Thirty seconds to spacecraft set. Everything looking good. Ten seconds to spacecraft set. Everything looks good. Rates nulled out. We have spacecraft separation. Both brake wires indicate MAVEN has successfully separated from Centaur. Everything looking as expected. We are reorienting to CCAM. And with the successful separation of the MAVEN spacecraft, this concludes the commentary for the launch of AV-38 with the MAVEN spacecraft.
And we're now 53 minutes, 18 seconds into the flight of MAVEN. MAVEN is now cruising on its own. We will be having our NASA Launch Director, Omar Baez, come over very shortly and talk to us about how the countdown and how the flight of the Atlas V went. The spacecraft over the next hour or so will be going through a number of activities, including deploying the solar arrays and going power positive with the sun. And we will have a spacecraft status at our post-launch news conference scheduled for 4 p.m. So at this point, all of the data indicates that we've had a very good flight of the Atlas. We'll have Omar Baez come over and talk to us about that here in just a moment. And MAVEN is now on the way to Mars. So we'll be standing by now. They are watching carefully data that will be coming in through the Canberra tracking station. And the Perth tracking station in Australia is also actually the station that makes the initial acquisition of MAVEN before it passes over Canberra.